variance. Now we're going to get sophisticated. Let's just kick off with a nice little example here. What is the expected value of the number of empty bowls from that last example? What's the expected value of the number of empty bowls? Another way to say that is, what is the mean? Oh gosh, what do we mean by that? What I mean is, if we were to perform this little ball tossing in the bowl experiment 1,000,000, 100,000,000, 1,000, 1,000,000,000 times, over and over and over and over again, on the average, how many bowls are going to be empty? Okay, so this is the notation we use for that. You read that as the expected value of x, the expected value of x. Okay, it's a functional of x. Remember, so a functional is a function of a function, and so this is remember, technically x, a random variable, is actually a function from a probability space to the real line. So this is an example of a functional. Okay, it's so this thing is the expected value of x. Okay, also the same thing as the mean of x. So for our example there, it's shouldn't it just be, gosh, how many empty bowls can you have? You could have no empty bowls with a probability of 36 out of 81, or you could have exactly one empty bowl with probability 42 out of 81, or you could have two empty bowls with probability 3 out of 81. And what does that work out to be? Well, that's the first term is 0, so I've just got 42 divided by 81 plus 6 out of 81, and that's comes out to be about 0.59259, approximately 0.59259 or so. Okay. Now notice that that is not an integer. That is not an integer. Don't feel compelled to round that number, please. Okay. Do not round that. Of course, you can't have 60% of a bowl being empty. Of course, you can't have that. When you do this experiment, you'll get no empty bowls, or one empty bowl, or exactly two. It doesn't matter. This word expected value, or expectation, or expect, it has a different meaning than it does in day-to-day life. You would never honestly expect to see 60% of a bowl being empty. Well, you know, when you do this experiment. Better example is, maybe you would never actually expect to see half of a person in an elevator, right? That'd be kind of gross. But, you know, on the average, maybe you have an elevator that only has about half of a person in it. On the average, okay? It's the average number of people who are in the elevator per time or something. In this case, this is the average number of empty bowls when you do this experiment over and over. All right, so let's write down a real definition here for the expected value. So, the expected value of a random variable, for a discrete random variable, we'll stick to the discrete case, is defined to be the sum over all possible values that that variable can take on times the chance that the variable takes on that value. It's nothing more than a weighted average. You see that? You're summing up all the possible values you can take on, but multiplying against the probability weights. Okay? It's the same thing as, you know, if you're taking a course, you know, how do you get your final grade average? Your final grade average is it's just a weighted average of your homework, right? Your homework, maybe that's worth 20%, plus exam 1, which is worth 20%, plus exam 2, which is worth 20%, plus exam 3, which is worth 20%, plus maybe your final is worth 20%. Your final exam is worth 20%. Okay? All right. That's exactly how all your teachers have always done your grades, right? Maybe these percentages are different. Maybe you've got 10% for the homework and 30% for the final exam, or whatever. But it's just a weighted average, right? Where the weights are the percentages, and the weights, guess what? By your probability axioms, it must sum up to 100%. Okay? It's the same thing here. It's exactly the same thing here. You should note that, and this is important, that the expected value is the same. It's the same as the center of mass. Okay? That is, the formula for the expected value, or for the mean of a distribution, is exactly the same calculation as you make for center of mass. I'll show you some software here in a little bit and sort of point out some things to you there. But it'll be meaningful for you, I think. If you think about, if you have, a random variable that can take on the value of, say, 0, or sometimes 1, or sometimes 2, or 3, where do you put your finger to balance all this stuff? I don't know, maybe you put it like right about there. Okay. If I averaged all this stuff, if this was like 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 2, 3, 4, 5. So I've got 5 zeros, right? Let's make a little distribution table. X can be 0, or 1, or 2, or 3. What's the chance that that this random variable takes on the value of, say, 0? It's going to be 5 out of how many? 5 out of 5 plus 8 is 13, plus 3 is 21, plus 2 more is 23. 5 out of 23. The chance that it's 1 is 8 out of 23. And the chance that it's 2 is 3 out of 23. And the chance it's 3 is 2 out of 23, right? So what's the expected value of X in this case? Well, it's going to be 0 times 5 out of 23, which is, well, that's 0, plus 1 times 8 out of 23, plus 2 times 3 out of 23, plus 3 times 2 out of 23. Okay? Whoops, I made a goof, didn't I? Should be dividing by 23. If I've got 5 and 8 and 5 there, that's 10, that's 18. It should be 18, shouldn't I? That's what I get for that's what I get. That's just what I get, folks. Let's do that again. Okay, 0 plus 8 out of 18 plus 2 times 3 out of 18 plus 3 times 2 out of 18. Okay? Alright, looks like 1.1 repeating. 1.1 repeating. Alright, so here's one. I guess it's somewhere in there. Look, I had a pretty good guess, right? That's where you put your finger to balance all that stuff. Yep, that's exactly what you do. It's the center of mass, or the center of gravity in this case. Okay? There's a difference there, but that's the deal. Okay? That's the deal. Now, what if we're interested in a function? What if we're interested in a function of a random variable? Okay? And what's the expected value of that? Okay? Well, so here's a theorem for you. Let's let x be a random variable. And g be a function. Okay? Say from the reals to the reals, maybe. Okay? Then it turns out that the expected value of g of x is, guess what? It's just going to be the sum of all the function values times the chance that x equals k. All right? It's just a weighted average of all the function evaluated at all the possible values of the random variable. And it's pretty straightforward. The proof is pretty easy, and I'm not even going to do it. It's in your book. But there's a little subtlety there. I'm going to say proof, C book. Okay. Note, however, that G could, it is possible that G is not a one-to-one function, okay, and in which case, you know, you may have different, you may have multiple values there for the same, or you may have you know, for different values of your random variable that it takes on, you might have the same G function, okay. So, take a look at that proof. Next thing we want to define is the variance. Okay, so if x is a random variable, okay, then the variance of x is defined to be the expected value of that random variable minus its mean quantity squared. Okay. Now, by the way, your book and sometimes people will use instead of the expected value of x, they'll write mu for the mean, the Greek letter mu for mean. It's popular. It's easier to write than all this stuff. Sometimes they'll put a little x down there to denote that, hey, we're talking about the mean for the random variable x, because sometimes we might have more than one random variable lying around. Anyway. So what is this? Boy, this is complicated. No, it's not, actually. It's not so bad. If you've ever had physics, or even if you haven't, this is related very closely to a quantity called the moment of inertia of an object. Look at what this is doing. So let's draw you a little picture here. What if I had some weights here and there, okay? Maybe I'm really talking about a random variable. Maybe this is 10, and this is 12, and so this would be 8, right? So what? Looks like, you know, half the time we see 8, half the time we see 12, okay? Something like that. Well, let me draw you another picture. What if I had something like this? Okay. Now, altogether, this is sort of weighted 4, right? You could think of it like that. It's like 4 pounds, okay? Altogether, this stuff is weighted like 4 pounds. Now, what would happen if I took this stuff and if actually it's sitting on a disc and I spun it around, okay? Right? It would spin at a certain rate, right? But then now what would happen if I, you know, came up here and I moved those masses out to the edges and spun it around? It would spin around at a different rate, right? Do you ever do that experiment where you get up on top of a circular platform and you have someone spin you and you move your arms in and out like that? And when you move them out, you move slower. And when you pull them in, you spin really fast, like an ice skater, right? That's because you're changing your moment of inertia there, okay? You're changing your moment of inertia when you do that. You're changing the variance is what you're doing. Same thing. Well, it's almost the same thing. Take a look at what the variance is. You're finding it tells you to find the average squared deviation from the mean. Both of these have mean of 10. Right? Mu equals 10 and mu equals 10, right? The mean is 10 for both cases. But here, what is the deviation from the mean for this value? It's going to be 2, right? And this one is also 2 away. And this one has a deviation of, let's say, -2, and this one has a deviation of -2. Okay. Now it turns out, see, what we're trying to do here is to try to measure the spread outiness of our values here. It's not a good idea to just average these numbers, because it turns out when you average these 4 numbers, you're always going to get 0. And that happens for every single random variable in the planet. Okay, so Instead, we need to turn some of these numbers positive, and we can do that by squaring them or taking absolute value, but that's not very popular. We'll square them. Okay, so what do you do if you square them? Well, you get some squares, right? Whoops, like that, right? Negative 2 squared is 4, negative 2 squared is 4, 2 squared is 4, and 2 squared is 4. So this is 4, this is 4, this is 4, this is 4. This pen is out of ink. All right, so this is 4, this is 4, this is 4, this is 4. Okay, so I've squared all those deviations, and hey, guess what? They're all 4. So actually, it looks like here the variance is 4, right? Because it's the average variation there. What about here? Here I've got this one is 1, right? And this one is negative 1. And these two are both 0 away from the mean. So what do you think the variance is down here? The variance is going to be, well, it's going to be negative 1 squared times the chance that it's at negative 1, right, which is a quarter, plus 1 squared times the chance that it's 1 times a quarter, plus 0 plus 0. Okay, so it's what is it? A quarter plus a quarter. It's a half. Half is a lot less than 4, isn't it? Yeah. So the variance is an attempt to measure how spread out the values are in a distribution from the mean, specifically from the mean. Okay. So that's what the variance is about. Now let me write that definition one more time over here, because I want to be clear about what this is. So it's the expected value of the squared deviation from the mean. So I could write it like that, right? So so remember we had that previous theorem that says it tells us how to write down the expected value of a function of a random variable, and this is a function of this random variable, right? This I could think of this. This is really like g of x, where g g of, say, little x is the function x minus mu sub x y squared. Okay, so then what the variance is? So this variance here, the variance of x, is you can write it as the sum of over k minus mu sub x squared times the probability that x equals little k. It's just a weighted average of these things, the squared deviations from middle. That's the variance. By the way, one more thing. Sometimes you hear people talk about the standard deviation. The standard deviation of x is written like this. It's a lowercase sigma. And sometimes we'll put a little x there to denote that it's the standard deviation of the random variable x. And it's just defined to be the square root of the variance of x, okay? So it's just the square root of the variance. It has an advantage over the variance in that it retains the original units of the variable that you're working with. And it's useful for measuring distances between values from the distribution or values from the mean and so forth. So you'll find a lot of statisticians like to talk about standard deviations, and a lot of probability people don't, or maybe they talk about the variance instead. Okay. Note that both quantities are positive. If you have one, you can get the other. Okay, not a big deal.